Today we are very kind of glad to have Jianwei Yang interviewing with us. And Jianwei is from Georgia Tech. His advisor is David Parrick. Yeah, David Parrick. Very famous for VQA and many kind of vision language tasks.
Jianwei cannot pronounce
it. So. Jianwei's research is mainly focused on computer vision, including object detection, scene graph generation, relation detection, this kind of thing. Focus on this topic, Jianwei do a lot of interesting work, including in the very basic stuff like to understand the image, to generate, to build a scene graph for image, and also apply them to visual language navigation, apply to kind of how to actively in their object detection, actively in their kind of question answering, this kind of problem. Also, Jianwei works on image generation based on his graph, image scene graph idea. So I will give more time to Jianwei to introduce his work. Okay, Jianwei, please.
Okay. Thanks a lot, Pengchuan. So yeah, I'm very glad to be here again to introduce my work. And so this topic is about a structured visual understanding and interaction with human and the environment. So as we all know, the world around us is highly structured. So for example, take this room as an example. So we can see a lot of chairs and the tables, and we have a bunch of us sitting on top of the chairs and lean on table. So actually, when I talk about this, actually in my mind, I already constructed a structure about the whole environment. And I know, okay, there are a bunch of objects, and there are some interactions between the object and also even for a single child, actually we can notice, okay, there is a child arm, there is child legs. So this kind of structure actually exists surrounding us everywhere. So similarly, actually, images are 2D projection of the 3D world. So that's why actually for each of the image we can observe some structure. For example, in the image we can see a bunch of objects, and also the relationship between the object, and even besides the foreground object, we can see, okay, the background actually is also contains some semantic information. For example, the grass, for example, the sky, for example, the sea, etc. So my whole research during my PhD study actually is motivated by this kind of motivation. So to model the cross-image structure, so we proposed a model called joint unsupervised learning model to learn to cluster the images and also the representations from these images jointly. So finally, we can see, given a set of images without any labels, we can construct some cross-image structures for the whole data set. So on the other hand, given a single image, actually, we can also model the pair image structure. So based on this motivation, we propose a graph async to extract the scene graph from a single image, so which consists of the foreground object, the relationship between the object, or even the attribute of each object. So furthermore, so what if we have a single object? Then we propose to use a neural communication network to model the relationship between different parts of the model. Specifically, we regard each of the channel in a single convolution layer as a part or pattern detection. And then we enable the communication across different channels so that it can learn more compact and complementary neurons for detect or classify a single object. So based on the pair image structure motivation, we further introduced a model called LGAN to learn to generate an image layer by layer. We first generate the foreground, we first generate the background, and then we generate the foreground one by one. And finally, we model the relationship between foreground objects so that the whole image layout will be reasonable enough. So on the other hand, based on the pair image structure, we want to model the interaction between the visual system and the human through the language. For example, given a scene graph representation, we can describe the image more visual groundedly. That's why we propose a neural baby talk model to describe the image based on the detected object. On the other hand, so to enhance the visual understanding of the image, we further propose a model called visual curiosity to learn to ask questions about the image, to gather the information about the image, to help to refine the visual understanding model. Finally, we want to model the interaction between the visual system and the environment. In this model, we want to enable the agent or the visual system to move inside a 3D environment, because as we all know, object in 2D image is usually occluded by some other object or some other stuffs. In this way, what if we can enable the agent to move around the occluders, and then we can get a better visual understanding of the object or the whole structure of the environment. So in this talk, I will mainly talk about these three work. So the first one is how we extract the structural representation from the image, and then how we build the interaction between the visual system and the humans through the language. And finally, I will talk about how we build the connection between the visual system and the environment. So I will first talk about the scene graph generation model. So this is our paper from ECCV last year. So what's a scene graph? So let's say we have an image like this. So this is an image from ImageNet. So we can categorize this image as a single label, for example, a king crab. But what if we can also actually detect all of the objects in this image? And finally, we can even model the relationship or annotate the relationship between the object. So for example, the man hold a king crab, the woman look at box, etc. So why we need a scene graph? So let's say we have two images in these slides. The left one and the right one both contain two objects, the man and the horse. But the difference is that the left image actually, the man and the horse has a relationship like walking, and the right image actually has a relationship like feeding. So in this case, actually, modeling the structure of the image actually help us to distinguish the images more accurately. And again, we can also describe the image more groundedly. For example, if we know the relationship between the object, actually we can describe the image more accurately than if we do not know the relationship between the object. And also we can answer questions more precisely. So if we know the relationship, of course we can answer the question more groundedly and more precisely. And finally, even we can generate questions more groundedly. So if we know there is an object, man, and there is an animal, but we do not know the category of the animal, but we know the relationship between them is walking, then what animal is a man walking with? Maybe let's say there are another horse on the left side, but there is no relationship between them, like walking. So this kind of question generation will be more beneficial from this structural understanding of the image.
And there's an interesting point. So for the kind of grounded question answering, the previous example, can you go back to? Yeah, you can see that, in fact, in this case, it kind of, to answer the question, it does not need to understand the relation, because there's only one horse there. What it needs to do is just, okay, detect one horse. If the horse is there, then just predict a horse or just say yes.
Yeah.
So,
It's better to have multiple horses.
Yeah, that's what I just mentioned. Yeah, there are multiple horses. Maybe a horse on the right side and a horse on the left side, and there is a relationship between the man and the horse at the right side, but there's no relationship between them. Maybe they're just far away, and then, yeah. So this kind of question actually can help us to understand or help us to refer the horse at the right side instead of the horse in the
Actually, we are
left side.
exploring how to use the SGG to improve the VQA task, but it will be we find it tricky to identify the portion of the VQA question, VQA task, so that can show the benefit.
I see.
Of this SGG.
I think I will talk about later. Actually, we also have a work, ongoing work that trying to propose a neurosymbolic graph reasoning model on top of the scene graph. And we found some interesting is that if we improve the scene graph generation model, the performance of the VQA performance actually improve as well. So from our observation, for example, if we use a very poor scene graph generation model as an input, and then the GQA performance or the VQA performance, yeah, we work on the GQA, and the GQA performance actually is not good. And if we improve the scene graph generation model a little bit, and then we can find that the performance of the GQA is also improved. So
Have we ever worked on the GQ?
we are working on GQA.
Using
yeah, I think we can talk about later. Actually,
Actually, VQA dataset is quite, the questions are quite simple, just like this question. You do not need to understand every detail.
Yeah, that's right. Yeah, and but I still think if we can do it in the neurosymbolic level, so actually we can make the model more interpretable, and we can easily diagnose which part of the model is wrong. As this part, I still believe.
That's fine. But we also want to show the improvement.
Right. Yeah. But I still believe because we know that the upper bound is very high. Okay.
Jim, so when you mentioned you are using a cracker single generator for the GQA, and then you improve it to get the improvement on the GQA. So do you think the GQA is a data set that is designed to show how good you are at the reasoning, or how good you are at just your vision backend? You have better object feature, better relation features, you get better results.
I think that depends, right? So because reasoning, most of the GQA model actually do not explicitly use a reasoning model. So they just use a previous model, like the model work well on the VQA dataset. And on that dataset, actually, they just simply extracted the features and from the image, from the question, and then they just combine with some attention model, with some bilinear kind of operation, and then they finally get the answer by classification. But I still believe that to finish this kind of task, for example, the GQA task, actually, the goal is that, so we have a better understanding of the image. I think this is a basis for us to reasoning. Otherwise, actually, we do not understand the image, and then the reasoning on top of it is not grounded. So that's why I think both of them are very important. So we needed to understand the image fully and completely, and also we needed to understand the reasonings in the question completely. And then finally, we can perform the reasoning on top of these two inputs. And that's what I think about the GQA data.
So regarding this discussion, I'm thinking that maybe it would be better if you were grounded in some sort of a realistic application, something that people would actually do instead of these data sets. Because you can have an improvement on a data set specifically built so you can show an improvement for your technique, but for what purpose? So it would be interesting to hear your thoughts about where would people actually be using these things.
I see. I really have a experience. So, for example, a simple experience is that so when I go to a supermarket, I want to find something, right? And then I needed to ask some person in the supermarket to help me to find. So I want to I want to find a bottle of Coke, and then I do not understand. So where is the place I needed to go? And this way, actually, what if we can build a structure or a structure map for the whole environment, and then I can ask the system, if I want to find a Coke, and then we have a good guidance from the system so that it can help me to find a Coke through, it can tell me the path towards the place so that I can find the Coke. I still think this kind of application highly rely on the understanding of the question. So, for example, different. So, what if we want to find some kind of other things? So, which means that actually we need the model to understand the question and also understand the environment. Of course, in this case, the environment is just an image, but a lot of different applications that the environment will be more complex. And then how to get the structure of the whole environment actually help us to build a model that can reason on top of the questions.
But you don't need the scene graph for that, for what you just described.
Yeah, so basically the scene graph actually, it's a kind of relational graph, but it's not a scene graph, right? Yeah,
I think in Jianwei's third work, he will talk about interaction with 3D environments. So I think you will be. And we were looking forward to that. So let's continue.
Okay. Yeah, and actually for the scene graph generation, the general pipeline behind this actually can be summarized by this figure. So given input image, we first extract the regions based on, for example, the region proportional network. And then we have two branches. The first branch is object feature. The second branch is a relationship feature. We do the RY pooling on top of the bounding box or the union of the bounding box. and then we get the object score, we get the relationship score, and finally we can generate the scene graph for this image. So there are some initial previous models, like we can updating the feature of the object and what is the relationship by performing some kind of message passing. For example, use the getted recurrent unit or some other kind of method. And furthermore, we can add extra supervision to the model by adding the region captions for each of the bound box. And by this way, it can further improve the training of the object features. And also, we can add some kind of prior frequency or prior knowledge on top of the model. So we can summarize the relationship pairs, a relationship based on the object pairs, and then we can plug this kind of information to the model for help the training of the whole system. So in our model, actually, we have two new parts. The first part is that we do the message passing on top of the feature level and what's the score level. And also, we add a relation proposal network here to extract more reasonable relationship pairs from the whole candidate pool. So the motivation behind this model is like, first, objects in the scene usually have relationship with others. For example, a simple case is that the car has two wheels, and two cars is next to each other. And also, not all object pairs have relationship. The scene graph is usually sparse. For example, the person at the left side and the car at the right side actually can be hardly described by some relationship. And the existence of the relationships highly depends on the object category, and the type of the relationship highly depends on the context. So based on this, we propose a model. And first, let's assume that we have a region proposal network already, and we extract one of the bound box, and then we compose a dense graph because we do not know which pairs has a relationship or not. And then based on this, we use a relation proposal network to prune the dense graph to a sparse graph. And on top of this sparse graph, we propose attentional G-scenes to help to propagate the information across the sparse graph. Finally, we can get the scene graph. So in this model, actually, we can regard the relation proposal network as a hard attention because it directly prunes the dense graph to a sparse graph. And the attentional graph convolution network actually is kind of soft attention model. It's attend the sparse graph and it adjusts the connection strengths for the sparse graph and finally do the propagation. And we can factorize the whole object function into three parts. For the region proposal network, actually, it's given an image and then it's extract the vertex for the scene graph. And for the relational proposal network, actually, it gives the image and also the vertex, it's extracted the edges for the graph. And finally, given the image, given the vertex and the edges, we finally perform the graph labeling to get the final result. And that's the scene graph. So let's briefly introduce each of the module. Actually, to save the computational complexity, and we propose a very simple way to do the relation proposal work. The first step is we compute the relationship needs between the subject and the object. And we use a kernel function to first project the relationship feature to two different space, and then we compute the similarity, just use an inner product. And finally, we sort it, and then we just choose the top key to use, and then compose a sparse graph. And the second step is we just use an NMS for the object pairs to do the filtering. On the other hand, the attentional G-scene actually is trying to perform the propagation across the graph. And the original G-scene layer is kind of like this. So we can see that the important part in this formula is that the alpha is not lineable or it's predefined affinities, because it's usually used in for example, the social network. We already define the connections. However, in our case, we do not have this kind of prior knowledge. So based on this motivation, we want to learn the affinities by this way. And based on this length affinities, actually we perform the object representation updating based on this kind of formula. And then we also perform the predicate representation updating based on this formula. So we plug in this kind of attentional GCN on top of the feature level and also the score level or semantic level.
In fact, this part, the attentional GCNs kind of have some kind of analog to the previous image passing method for the single generation. Can you do a very brief? Can you kind of briefly connect your single kind of this method to the previous image and message passing methods?
Yeah, I think this part. So I still think compared with previous work, actually, the attentional GCN itself, the goal is the same. So all of the model, including the previous model, actually, the goal is the same. So we want to propagate the information across the scene graph. And here, the difference is that we want to reduce computational complexity. And we found this GCN actually can help to propagate the information across the sparse graph and also can significantly save the computational complexity. And this is the first thing. And the second thing is that, so actually, as you can see from my previous slides, we apply this attentional GCN on top of the semantic level representation, which means that we directly take the probability distribution over different object category, predicate category as input. And finally, in my later slides, I will show that actually we can directly learn some kind of common sense or co-occurrence between the object or object and the predict in this semantic level attentional GCN. And I think this part is kind of interesting to show. I can show it later. Yeah.
So what is Z in the input? Like that, it's a vector of what? What are the
Yeah. So
the elements of Z?
Yeah. So actually in our model we have two meanings. So the first one, because we add this attentional GCN on top of the feature level, so which means that in this case, the D is a feature for each of the union bound box, which is the union bound box, which represent the feature of the relationship. And
So it's just the feature and not the identity of the object.
No, at the feature level, it's just a feature. And then at the semantic level or score level, this C is directly the probability distribution on top of the object category and the predicate category. And that's why we introduced two levels. And so we show later, actually the score level AGC actually can learn some kind of common sense from the data.
So you mean that if you use the image feature, in fact, you cannot learn the occurrence relation. But in fact, if you use the semantic level or label distribution, in fact, you can learn more useful information.
Yeah, I guess so. So in our experiment, actually we found directly apply the AGCN on top of the score level, actually it can already achieve almost the same performance if we combine these two. So I think this kind of model indicated that we can directly perform the information propagation on top of the semantic level instead of the feature level. So for the training of the model, actually, because we already factorized the whole object function into three different components, and then for the first part, we just use a regular binary cross-entropy loss. And similarly, we also use a binary cross-entropy loss to train the relation person work. And finally, we can use two cross-entropy loss, one for node and one for age, to perform the graph labeling. And metric. So the metric for the single graph generation is described as follows. So assume the n object extract from an image, then n times n minus 1 edges will be composed. And step 1, we take maximal for object scores and predicate scores, and of course excluding the background class. And then we compute the relationship scores by multiplying these three different scores. And finally, we sort these scores, and we computed the recall at 50 and 100 based on the ground truth and the predictions. Of course, if we want to solely measure the performance of the predicate classification, then we use two extra metrics. The first one is Fry's classification, if we assume the location of the object is given, then we just need to classify the bounding box and classify the predict between the bounding box. And we further assume that the category of the object is also provided. Then we directly, we solely focus on the relationship prediction of the model. And
so I'm not sure exactly what is an object in this sense. So earlier you had this example of the bird, and it looked like the scene graph had parts of a bird, like wing and foot and tail, that weren't necessarily in the photo. But are you counting those as objects, or is bird the object? Because tail, given that you have the head of a bird, you know where the tail is likely to be, right? So, or is it bird that's the object?
Oh yeah. So actually, in this single object generation model, actually we assume that so each object, for example, the bird and well maybe a cat is a single object, and this single graph actually describe in this single graph the node actually each of the node in the single graph represent an object, a single object, and then the relationship the edge describe the relationship between two objects. For example, a cat is sitting on top of the table, or a kite is walking on the road, or something like that. So, and which means that actually we assume that in the image, in a single image, there are multiple objects, and we want to model the relationship between multiple objects.
And is that inventory of objects one that you're taking from some set of object classification algorithms, or are you?
Yeah, these
deciding this
objects
yourself?
are predefined, right? Yeah. What's the number of the objects?
Oh yeah, the number of objects in this benchmark we have 150 object categories.
Yeah,
and
it's predefined.
Yeah.
It's like a vocabulary.
Okay.
Yeah.
But in fact, I think, for example, I think the objects are detected by you or proposed by your region proposal. But if your region proposal propose both the bird and its head as two boxes, then in fact the head will also be an object.
Be a node. Right. Yeah.
Okay, so the both head is
I
an
mean, sort
object.
of, maybe it's not worth diving down this. Related to Nebos's question, like, what is the scene graph for, I think, here? I mean, it's a little odd to me that tail and it seems like the inventory of sub-object labels is kind of arbitrary. You could just as well have lungs.
Yeah, that's true.
Whatever, right?
That's true. It's kind of a different level of the single graph. So we can describe the whole image which contain multiple objects into a single graph. And we can also describe a single object with different components into a graph. That's different kind of level or granularity of the,
I guess it's similar to a pension bank.
Yeah.
And then what's the basic unit?
Right.
It's a word or phrase or
Right.
name entity.
In fact, in this benchmark, there's a relation called part of.
So
That relation is really describing kind of head is part of the bird.
Sure, but you could get more and more granular.
Yeah.
Everything has atoms.
And the eye.
Okay, yeah.
Is the object proposal network pre-trained, or is it trained together with everything?
In our model, actually, we train it together. So the overall, as we
So
just
you just have the input, image as the input, and the output is the scene graph.
Yeah. So we train the whole model jointly.
But then you could actually run your whole model on ImageNet instead.
Yeah, we
So
can.
that you can actually discover parts.
But the problem here is that I don't think there are much annotations on visual genome describe the object's component. For example, the tail, for example, the wing.
Well, it doesn't matter. You could just say it's a bird. Model the bird using your model instead of convolutional network, so that you can actually learn parts.
Yeah, I think so. Yeah, I think we can learn to detect multiple parts and then to model the relationship between different parts. Yeah, I think that's doable. Yeah. And we work on the visual genome dataset, and as we just mentioned, there are 150 object category, and there are 50 predicate category, and we use different metrics to measure. So comparing with previous work, we found that our model has over 4-point improvement on single graph generation metrics, and the 2-point on SIGGRAPH generation plus, which we proposed in our paper. And due to the interest of time, I will not introduce the details for our new proposed matrix, but generally it's similar to the SIGGRAPH generation matrix. And the similar trend actually can be observed from the recall at 100. And there's some, like we just mentioned, so given an input image, we want to detect one of the objects. We want also model the relationship between the object, man, red wave, man in water, and man on surfboard, etc.
And in fact here, man has arm. This is kind of the relation.
Oh, yeah.
We always talk about.
Yeah, this kind of man has arm.
But not fingers.
Yeah.
One arm.
Yeah. And as I just mentioned, so there are some common sense images on top of the score level attention GCN. So I still think both of the feature level and the score level actually can learn some kind of co-occurrence. But the difference is that we cannot directly interpret the feature level AGCN, but we can directly interpret the score level AGCN. For example, if we sort the weight length in the attention GCN and rank it, and we can find that if we know there is a boat in the image, then it's very highly likely that there is a water or a beach. And then if there is a plane in the image, then it will be very likely that there is a wing and a tail in the image detected as well. So also similarly, we can learn some kind of object predict co-occurrence. And this is predict and object, so which means that, okay, we can learn hold hat, wear hat, and in boat, sit in boat, carry umbrella, hold umbrella. This kind of co-occurrence actually can be also learned between the object and the predict. And we also did some ablation study. So it's kind of very straightforward to see that our model, by adding the relation proportional work, actually it improved the last 3 metrics mostly. And by adding the attention GCN, it improved the first 2 metrics mostly. And finally, we want to dive into why it also improved the performance of the object detection. So we draw the average position for each of the object category. And if we zoom in the top ranked category, we found that, okay, racket, shot, windshield, and bottle, this kind of object category actually can be improved mostly. So we suspect that the reason is that because if we directly detect this kind of object, actually it's very hard because this kind of object is very small size and it's usually be occluded by some other object. But if we can model the relationship between the object, then actually we can use the context contained in the image and further improve the performance of the object detection.
So in fact here you are saying that your single generation model even do better than previous models on object detection.
Exactly.
But you can at the same time do relation detection.
Yeah, exactly. Yeah. And some take-away message. So first we introduce a general-based model it's kind of a skeleton model for the SIGGRAPH generation, and we found pruning the fully connected graph is important for SIGGRAPH generation. I think the reason is twofold. The first fold is that we can save the computational complexity by pruning the dense graph to a sparse graph. And the second is shown in the experiment. By pruning the fully connected graph, actually the performance will be further improved. And also, we needed to explore the context across object and predict. This is very important for us to improve the SIGGRAPH generation and also the object detection performance.
Jim,
Yeah.
2 slides before this. So I missed this part. So you meant that when you add the relation detection head, so it will improve the object detection as well?
Yeah, it will improve the object detection performance. Yeah.
But not by much, you said.
I think it's
Except
still.
for these smaller objects.
Yeah, for the small object, it's more significant. Yeah, and for some other, for example, the large object or most frequent object, maybe the improvement is just a little bit more, or even degraded a little bit. Yeah.
Could it be the reason that for those objects there have not been much relation annotation in your data set?
Yeah.
These ones there is more.
Yeah, I think that could be a reason. Yeah, I agree. Yeah, that's probably.
So intuition about the size is the right is the right intuition. There is, in all of this, there's an issue with not having the right balance between dimensionalities of the modalities. So if you repeat all these results at a resolution that's 2 times smaller in each dimensions, you would have different results. More things would require relations. Or if you didn't run it on pixel level, but you had the object proposals, but then you calibrate your object proposals based on the observed error rate, then again you would see a bigger advantage.
I agree. I think that's a good suggestion. So yeah, if we can change the size, and then it's probably get a better result. And but generally, I think the core idea behind this is that the relationship, or we build a connection between different objects, can generally help the performance of the object detection. I think a previous work that do not use a relationship, but to directly model the interaction between 2 different objects, even without any annotation of the relationship, then it can still improve the performance. Yeah.
I think it would help much more if you actually went into subparts, smaller things, detecting targets by finding little pieces and figuring out the relations. Rather than getting an airplane and saying there's a man in front of the airplane. I mean, you're not going to get much out of relations there.
I think so. Yeah, I agree. Yeah.
One more question. So Jim, here means that when you are doing the relation prediction during training, you are also fine-tuning your object detection backend?
We directly, because we jointly train the whole model. So basically, we just train the whole model from scratch, and we observe this. So we compare this model with a model with an object detector that directly trained without any relationship annotation. So both of the models are trained from scratch jointly. So, and we do not do some kind of stepwise training.
So you mean you don't pre-train an object detection, freeze it? And
Yeah. There is no fine-tuning process.
You do object detection and relation detection at the same time?
Yeah. We do not fix the object detector and then we fine-tune it based on our scene graph. Instead, we directly jointly train the whole model.
How do you manage the number of proposals, though? If you're training everything all together, how do you manage how many proposals you're going to have per image?
So in our case, the region proposal for each image is 256.
Oh, you fix it?
Yeah. Okay, so let's go to another work. So, and let's see, what if we do not have a good structural visual understanding solely based on the annotations? Then what if we can enable the visual system intact with human so that it can ask questions about the entities in the image? So visual curiosity, we want to learn to ask questions for the agent to learn visual recognition. So let's say we have an open world recognition problem like this. If we bring some kind of visual system which is pre-trained on ImageNet or MS Coco, and then maybe it cannot recognize some object like this. And but this way, what should I do? So actually, we can learn some kind of model, enable the agent to ask questions about this new concept in the new environment. So let's say, okay, so what is the orange object to the left of television? Because, for example, the MS Coco actually already have the television category, but it does not understand what this. And then it will ask, okay, what's the orange object to the left of the television, or something like this. And then, okay, that's a candle. And based on this information, it will go back to tune its visual system to learn about this new concept. And for example, hero, actually, in this kind of question, actually, it's needed the agent to get a reference, the television, and it's needed to understand the relationship between this new object, and the television.
So why a question like that and not what is that, and you just show the bounding box around it?
Yeah, I think that's a good question. So basically, we assume that it's kind of a visual system or even a robot move in the 3D environment, and then it shall move here. But if we have a screen, or even if we have an arm for the agent, then we need, for example, we want to directly ask the person, okay, what's the category or what's the attribute of the bounding box? Actually, this the person need to stay with the robot always. And then it's kind of course, it's a kind of a way to teach the robot, but another way is that what if the person and the robot actually, the person cannot see directly the screen or the finger or the arm of the robot? Then in this case, it's more like a two-person communication with each other.
If the human doesn't see anything, then how does the human know what the robot is talking about?
Because the robot will ask a question, right? And then let's say there is a robot here and there is a person here, and then okay, so the television, okay, the human already know.
The human and the robot are both in the room.
Yeah, exactly. Yeah.
And so then the human can see what the robot is talking about because the robot can go to the object, point at it, and say, "What is this?"
Yeah. I think that's another kind of way. But we assume that in this case, actually, we do not need the robot to move specifically to the target object, and then it can stay anywhere it like, and then just mention the object by asking a question, and then the
But
human
it
can
can
stay.
also point. It can also point.
Yeah, it can
Which
point.
is, that's what a child would do.
Yeah.
It wouldn't say, well,
Yeah.
what is the object next to the television
Yeah.
from the 50s?
Yeah.
It would say, what is that?
Yeah.
A child wouldn't know that that's a television, in fact.
Yeah, I think that's a good point. Actually, we previously thought about this. So actually, I really think a very natural way is that we combine the pointing and also the reference, because in some cases the pointing is not that exact. Because, for example, because it's a 3D environment, and then if we're pointing something, okay, so there is a distance, so the robot can, or the human cannot directly understand, okay, the object the human is pointing is in front of or behind. So by this way, we can combine the action and also the expression of the language to exactly localize or refer to the object. So that's our motivation why we need to develop this kind of model. And so the whole agent's architecture is like this. So let's say, as we just discussed, let's say the robot and the oracle or human see the same content or in the same room, and then the agent have a visual system, and it have a graph memory which maintains the information about the whole environment. And then given the current graph memory, it will use the question generator to generate a question and ask this question to the human or oracle. And oracle will provide an answer to the agent. And based on this answer, the agent will update its graph memory and then furthermore update the visual system, so that at the next round, the visual system or the agent actually understand the new concept, and then it will ask more about the new concept it do not understand. And so we have the visual system. So basically, it's not that complex. So we just extract the bound box, and we just model here. We only model the spatial relationship. And then we extract the attribute and object category and also the spatial relationship from the image. And finally, we can build a visual graph. Based on the visual graph, we can update the graph memory maintained by the agent. So we just do a simple neural symbolic copy, copy this kind of concept to the graph memory. And on the other hand, this graph memory will be also updated by top-down behavior. So let's say the oracle give an answer to the question, and then based on the answer, the agent will update its graph memory.
So can you explain in the what are different colors?
These two.
Yeah.
Oh yeah. So this is object category, and this is attribute. So different. Yeah. This because for each object we model we annotate the object category and also the attribute, different attribute. For example, the color or the material or the shape. Yeah.
So ideally, in the final case, like both the object distribution, the attribute distribution will be kind of a delta distribution, a very spiky distribution, which means that, okay, I nail down all the uncertainties and I learn everything.
Yeah, exactly. Yeah, at the beginning, it's just high uncertainty, very high uncertainty. So, but finally, we want to get some very peaky distribution, and also we want to ensure this peaky distribution is correct. on top of the.
Most of the questions are sort of clarification questions.
It's want to ask about a new concept or new object in the image. Yeah.
So this seems like a situation where, again, I think Nagoshi's comment, you could potentially leverage the scene graph, maybe go into a corpus of just natural language to try to figure out what that might be if you don't know what it is, if it's not in the inventory of objects that you know, to make some sort of informed guess rather than just ask what is the color of this thing, or what is this thing with this spatial and color signature. Where it seems like you could start to make informed guesses, like maybe not is that a candle, but is that a lamp or something like that, because I know that is typically where something that looks like that might be a lamp, might be living. But you're not doing that here, you're sticking to these higher level questions?
Yeah, I think that's a very good point. So in this work, we did not do that, but indeed, we can do like that way. So because we previously want to introduce a yes and a no question, which means we want to use this kind of question to clarify some entity in the image that the agent is not very sure, but it still can get some prediction. But finally, we do not add this yes and no question, because actually the training of the whole model actually is already very challenging for us, because we use reinforcement learning to train the whole model, and we found introduce this will introduce more difficulties, and that's why we did not add it. But yeah, ideally we should add some question like this. So for the clarification question, for yes and no question. Yeah, so that's a very good point. Yeah. And question generator. So we want to learn based on the graph memory as input, based on previous question answering, and we want to learn to get the target object and the target attribute, and also the reference object. These are three different elements, and based on this, we can pose some questions like this. So, for example, if the agent want to ask about this object, and then there is no reference, and then what is the shape of the frontmost large red object? If it already know it's a large object, it's a red object, but the shape it does not understand, then it will ask about this. And then it will also ask like this, but in this case we have a reference to this object, and for example, then it will ask about the color of the metal cube on the left side of a small object. And finally, we can further ask about object 5 in a similar way. And the Oracle side, the question, to answer the question, actually, it has different type of answers. First, if the question is answerable, so which means that, okay, the Oracle can understand this question, and then it will answer red. But in some cases, the question generated is not answerable. So what is the shape of the object at the left of the green object? Actually, there is no green object. And then it's kind of invalid question. Then the Oracle will tell the agent, okay, this question is invalid because it does not meaningful. And another case is that what is the color is a small cube. Actually, there are multiple small cubes, actually, here and here. So in this case, actually, the answer will be ambiguous. The Oracle will tell, okay, your question is ambiguous because there are multiple cubes in the image, something like this. And finally, we train the model, we train the visual system and the policy together. And so for training of the visual system, we use cross entropy loss between the graph memory and the visual prediction over more images, object, and attribute. And it's kind of basic conventional supervised learning. And we update the visual system after each dialogue with SGD. And on the other hand, we introduce a question of policy, and we train this policy with reinforcement learning algorithm. And we want to maximize. We want to maximize the reward over more images and the dialogue runs, so that the agent can ask as few as questions to the Oracle to get as much as possible information from on top of the image.
So what's exactly the definition of the reward? Because this is very similar to the kind of experiment design. You want to design the least kind of the least possible number of experiments to get kind of all the answers nailed down.
Yeah.
So I'm interested in what's exactly the reward function you're using here.
Yeah. So basically, this is a this is a reward at the time step t, because we want to increase the graph recovery, the information recovered by the dialogue rounds. So basically, this kind of this S measure the similarity between the current graph memory and the ground truth graph memory, and then we minus the current one by the last time step, and then we want to get the change of the graph of the graph memory recovery. And then based on this reward, actually we want to ensure that at each round, actually the agent can ask some informative questions to get more get a positive reward.
But this is more like an immediate reward.
Yeah.
But go back to your previous example, right? It's ideal to have a sort of global policy, which object to ask first, so that you can ask the next object using this one as a reference.
Right.
So how do you, maximize the so-called long-term reward or global reward?
We found that this reward is very helpful, and we only use this reward in our
But
training.
you also use the number of questions as a penalty, right?
Oh yeah, there is a
Another
penalty like
reward.
that.
So
Yeah.
Basically, you encourage the agent to ask smart questions.
Yeah, smart
So
questions.
Eventually, you don't need to ask a lot of questions.
Yeah. So we have a penalty on top of the number of step or dialogue round, and combining with this reward, these two together. Yeah.
Jim, you mentioned this reward is easy to play,
Yeah.
to game it. So why?
Because I think this kind of I think this is a problem in reinforcement learning. So actually, this kind of reward is kind of reward reshaping, because in this case, actually, each time step will have a zero reward or positive reward, and then most of the time so compared with a conventional reinforcement learning, actually the reward is obtained at the final state. But here, at each time step, we can probably get a positive reward. I think this is the most important thing why we can train the policy well.
This is the similarity.
Yeah, similarity. Yeah.
So you don't have to sort of sparsity.
Yeah, there is no sparsity about this. So that's why, we can train the reinforcement learning model. Yeah, I think that's very important. Yeah. And so this kind of reward actually, as we just discussed, so asking ambiguous or informative questions is kind of top-down. And also we need to learn a better visual system quickly based on the graph memory collected by the interactions with a human. So it's kind of bottom-up. So these two things actually are both very important for us to get a better performance.
Okay, quick question. For this one, do you take into account some vision recognition errors, so understanding errors? Because the vision system, this probably this object is green, red.
Yeah.
But there could be some mistakes.
Yeah. We consider about
this.
Yeah, we take this into account. Actually, the prediction from the visual system, as far as I remember, is kind of 80 to 90% accuracy, and it's not perfect.
This is similar to the normal dialogue system, right?
Yeah.
The dialogue agent needs to understand the user input, but there's a speech recognition error, natural language understanding errors.
Yes, exactly. Yeah. So there is some errors for the visual system actually. So, but the whole model actually we found it still can handle this without any diverge or something like that.
You can run experiments by artificially introduce some noise.
Yeah. I think that's really
Do
good.
they have two kinds of questions, like have invalid questions or have ambiguous questions with ambiguity? Maybe that kind of thing is that kind of question deal with the kind of error in the vision system.
Is that true?
These two is indeed very important. So from the Oracle side, so if in this case, actually the Oracle will tell the agent, okay, this question is invalid or this question is ambiguous. Actually, this will push the agent to derive more informative and unambiguous questions. And then, based on this, actually the annotation obtained or the graph memory obtained through the dialogue rounds will be more accurate. And that's why the visual system will be trained with more high accuracy. So, yeah, I think that's a good point. So we have two data sets, and the first one is synthesized data set. So we train our model on top of this synthesized data set, and then we directly test our model on top of this realistic data set. We want to check whether this kind of model can be directly generalized from a synthesized data set to a realistic data set. And finally, we found it works. And we compare with some baseline. So I think you might consider some baselines, like if we randomly select a target object, if we randomly select an attribute, if we randomly select a reference object. And then we also use a highest entropy selection strategy to select the object or attribute with the highest entropy in the graph memory. And also we combine the highest entropy and also the spatial together for the comparison. And we collect a standard data set. It's based on the clever data set, and we have different object shape, colors, material, and size. And normally the number of objects is from 5 to 10.
Yes, so sorry for you want to mention something there. So the task is to identify to clarify the attribute of one object or all the objects in the
What the object?
one object.
All the objects.
All
All the objects. So for each image, the agent will ask at most 50 rounds of question to the Oracle. And after these 50 rounds of dialogue rounds, and then ideally we want to measure how much the agent can recover on top of the image. Yeah. And we have, like we just mentioned, so there are 50 rounds at most. And then we measure, okay, so if the agent already asked the 10th round, and then how much information it can recover from the dialogue, and then finally we can get the recovery at the last round. And we measure different. So we compare the random and entropy-based, entropy plus context and hours. And finally we add a ablation study without updating the visual system. So as you can see here, so there is a very clear trend that our model consistently improved the graph recovery compared with the baseline model. And finally, we remove. If we do not update the visual system during the dialogue round, so what happened? So we confirmed that this performance is reduced much. I think this is a very reasonable result, because if we do not link the visual system for the agent during the dialogue system, which means that all of the information are stored in the graph memory, and the agent itself actually do not learn anything. It's just a memorization on top of the graph, and then of course the performance will degrade a little bit. And we further collect some data set. It's kind of a novel concept and a mixed and also realistic data set. And we only train our questionnaires on the standard set. And all of the other testing is directly performed without any fine-tuning or any other training. So as you can see here, there is this training on standard and test on standard test set, and training on standard test on the novel set, and the mixed one and the realistic one. So basically, we over these three synthetic data set, even it's novel or mixed, actually there is almost no degradation regarding the performance of the graph recovery. But on the realistic data set, actually there are some degradation, and we suspect it's not because of the model itself, it's because on the realistic data set, actually we have more object category, more attribute category on top of the realistic data set, and generally the performance will degrade a little bit. And for example, we just directly transfer our model on top of this realistic data set. It will ask what material is left most thing, and then it's food, and then the left thing, what is left most object, what is, and potato, and the leftmost object, what color, and etc. And then it will ask about the other object that need some reference, paper, and finally career. So there's some takeaway message. So in this model, we propose a neural symbolic pipeline to ask questions for agent to learn the visual recognition model. So through the interaction with human or the oracle, the agent actually improves its visual understanding capacity gradually on the fly. So finally, the learned question actually generalize very well from the synthetic data set to realistic data set. I think this is the advantage of the model itself, because we use a neural symbolic pipeline instead of a purely neural pipeline. And that's why we can simply generalize from synthetic data to the realistic data set. Okay, so finally, I would like to introduce how we can model the interaction between the visual system and the environment to help the visual system to understand the environment or the visual signal, visual data more better. And this is our paper from ICCV this year. And the motivation is like this. So given, let's say we have a visual system here, and at the beginning, it's just propose a region like this, and then it want to understand what's the category and what's the shape of this object. Of course, we can do it with a static visual system model, and we can predict it as well, but the performance may be like this. The result maybe is not good. And then what if we can enable the agent to move around the object? And then, okay, it's learned to, okay, so move move right, and then move right, and then move right, and then move forward, something like this. And finally, it can get a better visual recognition result. Oh, it's a sofa, and the whole shape of the sofa is like this. And this is our motivation behind the paper. And embodied model recognition, we introduced a new pipeline. It's called embodied model recognition model. So generally, the passive one is something like this: give an image, and then we predict the category and the segmentation result. And usually, it may fail to recognize the object. And then we propose an embodied model recognition pipeline. It's kind of combining the model recognition system, which is a visual system, and also have an action policy to help the agent to learn, okay, how to move to get a better observation. And we introduce EAR task. So it consists of 3 subtasks. So object recognition, 2D and model localization, and 2D and model segmentation.
So what does a model mean?
Yeah, so that's a good question. So a model means that the segmentation or the localization should also consider the part of the object which is occluded, and which means that we do not only just predict the visible part, we also need to predict the invisible part for the object as a total. And this kind of a model perception actually is kind of psychological observation and on top of ourselves. So in general, human has this kind of a model perception ability, but the visual system actually usually do not have this kind of a model perception. Yeah. And this is a model. A model recognition part is kind of temporal image processing framework. So the object function is like this. We have a visible bound box as input, and then we observe multiple images by moving, and then we want to predict the result based on all of this information when we get during the move. And we propose to use a GRU to do the temporal aggregation to get better and better results. And we use 3 different laws. Actually, these 3 laws is for classification, for bounding box localization, and for mask generation.
So you only guess the bounding box for the last image where you see the whole thing, but not for the first image where you saw only part.
Oh, we are predicting on top of the first image.
So your observations is I0, I1, and IT. Which one is the first image?
Oh, I0 is the first image. And this is not means, YT does not mean, okay, so this prediction is for the T image. So YT is the prediction at the time step T, and it's still for the first image. It's still...
I see.
Yeah,
so it refers to image
Yeah,
0.
yeah,
It's
exactly.
the T prediction.
Yeah, exactly.
So which means that the output segmentation is kind of laid on the image 0.
Yeah, I think this is a little bit tricky here, or even a little bit weird. But when we define this task, actually our motivation is want to compare our embodied or active vision system to the passive one. And for the passive one, actually it's only have the input, the first input. And then for the fair comparison with the passive visual system, that's why we also constrain our model, also predict for the first frame. But of course, we can extend our model to predict all frames, or the last frames, or even the whole, even the 3D shape of the object. Yeah. And lane to move. Similarly, it's also take the sequential image as input, and they want to learn some kind of policy to guide the agent to move. And we use reinforcement learning model to train the policy. To do this task, we collect a new data set based on the sensor G. So we collect 8 object category, and as you can see here, there are different kind of occlusions in the environment. For example, here, this is not that much, but this is severely occluded. And in this way, actually, the object is out of the viewpoint of the visual system. And we also collect the shortest path towards the target object when given the location of the agent at the beginning.
So a question here. So what you've shown so far, you are going to move around and then figure out what it was in the first scene and put the bounding box. But you also learn how to, in the future, predict where the object is and the things that you don't see, even without moving around.
Sorry, you mean...
So what I mean is, I see a chair, and I can imagine the rest of the chair here.
Yeah.
Right?
Yeah.
I can walk around and see it and verify it, but I don't have to. I can do it now because I've walked around before. So I know what the chair looks like because I walked around before. So in your system, is that your goal, or is it just the goal to backtrack?
What's the goal of the task?
Yeah, so the goal of this task is that, so let's say, so the goal of the task is trying to learn a action policy, so which can help any kind of system, a visual system,
to see the full object.
To see the full object, to understand the object.
Learn how to imagine what the full object is, despite the occlusions.
So for on the side of the visual system, actually we do not. So actually we focus on the action policy part, and regardless of the visual system. Actually, ideally we want to see that, okay, given whatever visual system you provide me, and then I can plug our action policy to help the original visual system to improve the visual understanding of the object. So this is our ideal goal. And now actually the visual system, actually we just train some visual system, and then we want to learn a better action policy to help the model, the visual system model, to understand the object better. So, which means that our goal is focus on the policy part. Yeah. And the result, let's see some result here. So we have 10 time step movement maximally, and then we compute the accuracy and the embodied bound box IOU, and also the mask IOU And we confirmed that the embodiment helps to improve the model visual recognition performance. So at the time step 0, and you can find the performance is not that good, and then if we keep move, and then the performance will be improved. And also our learned movement strategy for the agent actually outperforms the other movement strategy, for example, the random one or the shortest path one. And finally, we confirmed that actually the model recognition performance tends to saturate at the end of the movement. I think the reason for this is twofold. The first fold is that because we use a very simple temporal fusion or temporal aggregation method to aggregate the information from multiple viewpoints or multiple frames. And the second thing is that because the time step with the growth of the time step, then the training or the fusion of the information will becoming much more challenging. And that's why we can see some kind of saturation finally. But I think it can be improved by, for example, adding some tracking system to help to localize the object better. Yeah. And we also did some ablation study here. So as I just mentioned, so the aggregation actually plays a very important role. We compared with some average fusion or maximum fusion, and also we use the optical flow to help to do the feature warping between multiple frames. And finally, we combine the GRU and optical flow based feature warping, and we found that this kind of combination works best, although it's not that significant. And finally, we want to show the length actions. As you can see here, this is a distribution of shortest paths across different time steps. And the arrow pointing up is moving forward, and then move left, move right, and turn left, turn right, and move backward. So as you can see here, the length pattern is very different from the shortest path. And we can also observe this difference here. You can see here the shortest path, of course, is approaching to the target object, but our length path actually is not necessary to approach the target object. It's maybe just, okay, move, shift left, shift right, and move forward, even move backward, actually, and to help them understand the object. And let's see some results. Oh, sorry. So this is a passive one, the performance something like this, and then it will learn to move. Maybe in this case, actually, it's learn backward a little bit because the object actually is out of the scope of the agent.
So what is hallucinate?
Hallucinate is kind of learn directly to do the model perception based on a single image.
From paired examples.
Not a paired example. So it's just a given single static image, but with a.
When you're learning, though, you have paired examples.
Yeah. So for hallucinate actually describe the traditional static model perception. So which means
when you train it, you have that image, plus you have a label of where the bed is.
Yeah.
That makes sense, right? So
during the training, that's true. Yeah. During the training, we have the annotations, right? Yeah.
And so the other one is to actually figure that out without having examples, or do you still have examples?
We still have the example. Yeah. So, but the supervision is the same. The difference is that we plug a action policy for the visual system. Yeah. And due to the time limitation. So we will show some technical messages. So we confirmed that actually embodiment helps to get better visual recognition on top of the object in 3D environment. And we can also observe that our model actually learn a better movement strategy. And even though it's sometimes very challenging for us, but it still can improve the performance of the visual system. And finally, I think a future work on top of this is that what if we can enable the object, enable the agent to move inside the 3D environment and then get a full understanding of the environment, maybe even in 3D structure. So finally, to summarize, so in this talk, I just talk about our 3 works. The first one, how we extract the scene graph from a single image to perform the structured visual understanding, and then how we leverage the interaction with human through language to help to understand the visual data, and then how we leverage the interaction with the environment to help understand the visual object in the 3D environment. So basically, to summarize, it's kind of learning from interactions with human and environment. And furthermore, actually, we can also, instead of learning from ask questions, actually, we can also learn from the image corpus. And then, for example, given an image and a lot of descriptions, and then how we leverage this kind of description to help understand the visual data. On the other hand, actually, we can even model the 3D structure in the 3D environment and to help to understand the whole environment. On the other hand, actually, what if we already have a good structured visual understanding on top of the image or on top of the 3D environment? Actually, we can use this for interactions with human and environment. So, for example, this is one of our previous work, Neurobaby Talk. We extract the object and then we compose the description of the image. And also another work I'm doing now is called graph reasoning machine. So we extract the image, scene graph from the image, and then we extract the reasoning programs from the question side, and then we use an executor to get the answer. And finally, this is a recently very popular visual language navigation task, and we know that actually in this model, they usually do not have a structured visual understanding of the image. And what if we can extract the object, and what if we can get the attribute and even the relationship of the object? It might probably help the model to get a better visual language navigation performance. To summarize, so I think the vision as a whole actually is very important, and especially I think the structured visual understanding is very important. And on the other hand, so because the visual system is not solely isolated from the human or environment, we definitely need to model the interaction between the human and the visual system, and also the environment and the system to help to get a better structural understanding. On the other hand, it's kind of a dual problem. So what if we already get a structured visual understanding? Actually, we definitely want to use it to interact with human and the environment. For example, the task I mentioned in the last slides. So finally, we can get a visual system, especially a structured visual system that can get a better interaction performance with human and environment. And so basically this is one of my, this is maybe one of my future goal to work in my research career. Yeah, and finally, I would like to thank all of them. And without them, actually, maybe a bunch of work cannot be finished. And thank you.
So your relationships were all pairwise relationships. Do you think it's important to model relationships between more than 2 objects? Like who are all of the people playing together in a game or things like that?
Yeah.
Did you see that in the data sets at all, or are all of them pairwise, or do you think that it's important?
As far as I know, I did not notice any kind of this group relationship in the visual genome dataset. And but I still think it's very important to modeling the relationship between 2 groups. For example, so maybe there are 2 groups people to play the basketball. Actually, it's not between 2 single person. It's between 2 groups. And what if we can model this kind of even high-level relationship? Then we can capture more information from the image or from the video sequence. I think that's that's a very good point.
And then what do you think the challenges would be with extending your current approach to handle that kind of group setting?
I think the first challenge is that we can hardly get the annotations. So the first is about data itself. So recently, I think even for the visual genome, actually, it's very nice. And it's not a complete annotation for the relationship between two single objects. And that's why I think the first challenge is the data. So how to collect the data. So how we can annotate the relationship between two groups more completely and more comprehensively. And I think this is the first challenge. And besides this, so how to model the relationship between two groups. And I think it's still very challenging if we directly use any of these, the single object generation model I mentioned in my slides, because the problem is that so it's kind of hierarchical modeling. So we needed to first model the relationship between two single objects, and then we further needed to aggregate the information for each of the group, and then we model the relationship between two aggregated groups. And then I think the model, the reason model actually cannot be directly applied to this. But it's still a very interesting direction to explore, I think.
The application we have is a triplet. That's it. All triplet in the visual object.
I think you can do the graph traversal to include different objects.
And that makes sense. You
Right?
can
You can
do that.
define the scope of your traversal. Right?
Any other questions? So in fact, finally, I think we still have 3 minutes. I want to ask a very high-level question. Kind of from your kind of 3 work, especially the last 2, it seems to me that the project is so large, contains so many components, and I can hardly imagine that I can finish this kind of even one project within 1 year, because there are just so many components. So what's your experience to finish this kind of large scale, kind of many different components? You need many different skills to finish this project.
Yeah, I think
Good question.
that's a very good question. Actually, this reminded me the tough year I work on this kind of project. Actually, so actually these 2 projects both involved the reinforcement learning algorithm. I think maybe you also experienced the difficulty to tune the reinforcement learning model, and
it's not only reinforcement learning; it's vision, reinforcement learning, NLP. Many pieces composing together.
I think the whole overall looks very challenging, and actually, I'm not sure whether you notice. Actually, we simplify a little bit. So, for example, for the second one, we assume that all of the bound box is already provided. So there is no misdetection or mislocalization of the bound box. And for the third one, actually, we also simplify a little bit. We assume the visible bound box is accurately provided by the the user. And actually, these 2 simplification help us to get the model work. Otherwise, if all of the component is just learned or just provided from scratch, and then the whole model I can hardly imagine I can work it out. I think so. I guess in these 2 models, we do some simplification. I think this is very important. And
Sorry. Also, I want to learn how you collaborate with other members in your lab. So, for example, some of these require some system development skills. So it's hard to imagine you develop these 3 systems from scratch, right? It must be a teamwork.
That's true.
It's true in our team as well.
We
are working on multiple projects, several projects. Most of the project is some system development. So how?
I think in both this actually we have a lot of collaborators, right? And I think during the project actually we usually discuss a lot. So especially we just
we also share code.
Share code, and we have a shared GitHub repository. and different people can get access to the repository very flexibly. And this is the first one. And the second one is that actually different people have different kind of skill set. For example, Jason is more focused on vision and language combination, and I'm more focused on the vision side. And Stephen, for example, a postdoc, and actually focus on the high-level discussion. It's kind of he's very smart, and he can get us at a very high level. And usually, I found what he talked about is very reasonable and is correct. And actually, he helped us a lot as well. Yeah. So. And also for the last work, and Zhile and Minze, actually we discussed a lot. I think we discuss every 2 days and on top of the project. Actually, behind this model, actually we tried a lot of different model designs. Actually, so but finally we can make it work. I think it's kind of group effort. It's not just myself's effort. Yeah.
How about Anita Cannon? How do you know her? Anita
Sorry.
Cannon.
Oh, Anita. Oh, yeah. When I interned at Facebook, and she at that time she's a researcher at the field, and then of course she already left to create to co-found a startup, and we collaborate on the AR gun project for the image generation. Yeah, yeah.
Okay, so any other questions? Then let's thank the speaker again, and I'm looking forward to kind of talk with Jiang Wei one-to-one, I think. Okay.
Thank you.